Okay, we're going to continue looking at transformations by looking at horizontal stretches. Again, we've got the same parent function, y is equal to f of x, as defined in the graph and in the table of values that goes with it. And now, given y is equal to f of x, we're asked to graph y is equal to f of 2x. So again, just as before, we have to change the input value before we put it into the function. So we're replacing x with 2x. Let's take a look at what happens. So when x is -4, f of 2x means f of 2 times -4. And 2 times -4 is 8, so we're looking for f of -8. And we have to do that. We have to plug in the x value we're given, -4, in for x here, multiply it by 2 before we can evaluate the function. Now we've got f of -8. So we look up to the table above and ask, well, what's f of -8? Well, we're stuck because there is no f of -8 on the table above because the graph doesn't go that far. It doesn't go out to -8. So we don't get an answer for that one. And this new graph's not going to exist at the point when x is equal to -4 because of that. Let's carry on and see what happens. When x is equal to -2, we plug 2 in there. We get f of 2 times -2, rather. Is equal to f of -4, and this one we can evaluate. We look above and we get f of -4 is equal to 0. So now we know that we have the point -2, 0, which is going to be over here on our new graph. Now for x is equal to -1, we're looking for f of 2 times -1 is equal to f of -2, and looking above we see that f of -2 is equal to -4. So when x is equal to -1 on the new graph, we get -4 as our y value. So that's going to be there. When x is equal to 0, f of 2 times 0 is still just f of 0. And looking above, that's equal to 0. So that point goes there. And in fact, it hasn't moved. When x is equal to 1, f of 2 times 1 is equal to f of 2. Looking above, f of 2 is equal to 2. So now we have the point 1, 2 on our new graph. When x is equal to 2, f of 2 times 2 is equal to f of 4. And f of 4 from above is equal to 0. So now we have the point 2, 0 on our graph. And just to illustrate the point, when x is equal to 4, f of 2 times 4 is equal to f of 8, and there is no f of 8 in the graph above, so that point doesn't exist. And it makes sense, because if you look at it here, you can see that we've already got all the points from our function. So if I try and connect these, I get something that looks a bit like that. Okay, now let's look at what's happened to our points. First of all the y values here are the same as they were above. 0, -4, 0, 2, 0. Again, 0, -4, 0, 2, 0. So the y values haven't changed. What has changed are the x values. Notice that for any given y value, the x value that generated it is half as big as it was before. So here we had -4, 0, but now the point has become -2, 0. Above we had -2, -4, but now we have -1, -4. So the y values are the same, but the x values are half as big as they were. And you can see that on the graph because the graph's gotten pressed in this way towards the y-axis as the x values have gotten smaller. So the x values have been halved, but the y values are the same as they were before. So what that means is that we've actually got a horizontal stretch, or sometimes you'll hear it called a compression, of factor a half. We've actually stretched or compressed the graph in half towards the y-axis. And you'll hear different teachers in different books will use these. Some will prefer that you always talk about stretches, and some will use the word compression when they're talking about something getting smaller. But the idea is that it's still a stretch, or it's that kind of transformation because you're multiplying the values, but you're multiplying them by half. Now notice that this was a 2, whereas the factor is 1 over 2. Okay, that's a difference, and we're going to look at that with another example in the next video.